Standing wave ratio or SWR is essentially the report card for how well your transmitter, feed line and antenna system are matched. In amateur radio, achieving a good SWR is critical for maximizing radiated power and preventing catastrophic damage to your transmitting equipment. At its core, SWR measures the impedance match of your antenna system to the characteristic impedance of your transmission line and radio, which is almost always 50 ohms. When there is an impedance mismatch, the antenna cannot absorb all the RF energy sent to it. The unabsorbed energy reflects back down the coax towards the transmitter, creating standing waves of voltage and current along the line. Mathematically, voltage standing wave ratio VSWR is the ratio of the maximum peak voltage to the minimum peak voltage on the transmission line. While commercial rigs often have built-in protection, understanding and managing SWR is especially critical if you are designing, modifying or troubleshooting your own gear. Protecting the finals, power amplifiers. This is the most critical reason to monitor SWR. When reflected power hits the transmitter, it manifests as extreme voltage peaks and excess heat in the final amplifier stage. If you are homebrewing a 100 watt linear amplifier like the VU2 EVQ design using IRFP 150 MOSFETs, those transistors are handling significant current. A high SWR can cause the voltage at the drain of the MOSFETs to exceed their maximum breakdown voltage rating, blowing the transistors instantly. Alternatively, the reflected power turns into pure heat, leading to thermal runaway if the aluminum heatsink cannot dissipate it fast enough. Maximum power transfer. Your transmitter delivers its full rated power only when it sees a 50 ohms load. If you are operating a low power QRP rig like an AC Bitex or a Radio Berry SDR, every watt counts. A high SWR means a percentage of your hard-earned RF output is just heating up the coaxial cable rather than radiating out into the ether. Tuning and resonance verification. SWR is your primary diagnostic tool when building or modifying antennas. For instance, if you are trying to make an 80 meter wire dipole resonate on 160 meter without increasing its physical length, plotting the SWR curve across the band tells you exactly how well your loading coils or matching network are functioning. You tune for the dip in the SWR curve to find the antenna's true resonant frequency. What are acceptable SWR levels? 1:1 to 1.5:1, excellent. The system is well matched, less than 4% of your power is being reflected. 1.5:1 to 2:1, acceptable. Completely fine for general operation. Most modern solid state transceivers will operate happily here without folding back, that is reducing their power output. 2:1 to 3:1, marginal. You lose noticeable power to reflection and feed line loss. Solid state rigs will likely reduce output power to protect themselves. More than 3:1, dangerous. Do not transmit. Without a robust protection circuit, which many homebrew amplifiers lack, transmitting into this load risks immediate destruction of the final transistors. Now here is the antenna tuner myth. It is worth noting that using an antenna tuning unit in the shack does not fix a high SWR on the antenna or the coax. The ATU simply acts as an impedance transformer so that the transmitter sees a comfortable 50 ohms load. The high SWR and associated feed line losses still exist on the coax between the tuner and the antenna. Here is an interactive demo. This is the ideal situation. Source, load. Load impedance 50 ohms. Standing wave ratio is 1:1. Reflection coefficient is 0. And load impedance is 50 ohms here. So perfectly matched situation. Now we will see what happens when the load impedance changes. See, as the load impedance increases, standing wave ratio increases, reflection coefficient also increases. You can see the changes. You can see the changes in the reflected and forward waves and the envelope. Different color codes are shown here. And now if the load impedance increases further, say or to 100, then SWR becomes 2:1, reflection coefficient is high. SWR 3, great mismatch. Load impedance 150, source impedance is only 50. Reflection coefficient 0.5. When SWR is 4, reflection coefficient is 0.6. Corresponding load impedance is 200. That's a great mismatch. These are the conditions which we are to match using matching networks. Please remember that, as mentioned earlier, even if matching networks are used, the feed line still has that problem. Only radio sees an SWR of 50. Now we will see the other way around, below 50. It's around 50. As it goes down also, SWR increases, reflection coefficient becomes negative. Here the load impedance is 35, less than the source impedance. Source impedance is nominally 50 for the transceiver. See, when the load impedance decreases also, the SWR increases. Low load impedance is seen with Yagi antennas. When there are parallel elements, the dipole has lower impedance. That is, when there are parasitic elements, there is a decrease in the impedance. That's why we use matches like gamma matches for Yagi antennas. While the other end, this is seen with full loop antennas and other antennas which have a higher impedance. Folded dipole also has higher impedance compared to a standard 50 ohms impedance which is for the inverted V antenna. Even for the regular dipole, the impedance is not 50, it will be around 70. That means you will have an SWR of 1.5 or so for standard dipole, and for inverted V with an angle of around 90 degrees, that will be the situation where the antenna impedance is 50 ohms. So this interactive demo tells us how each changes, that is SWR, reflection coefficient, load impedance, and we presume that the source impedance does not change. Factory made source impedance is fixed at 50 ohms for the radio.